Welcome to Tomorrow Unveiled, where we condense the future into actionable insight. We've been digging through the research you sent over all these articles, policy notes, tech briefs, and honestly, one really clear theme just jumps out. A huge strategic global pivot towards high-density power.
That pivot is precisely what our research team is calling the green code hot core paradigm. It's a very clear signal.
A signal away from.
Away from prioritizing low density, variable power sources, the focus now is squarely on high density dispatchable solutions, reliable power.
Okay. So our mission for you today on Tomorrow Unveiled is to synthesize all that. We're pulling out the most critical findings, the real breakthroughs and policy moves from this past week, but only those corroborated across all the documents our team gathered.
Right. We want to build a clear roadmap for you, show where reliable clean energy is actually headed.
So let's ground this. Hot core, what exactly are we talking about?
Hot core refers to the tech delivering that immense reliable power. Think advanced nuclear fission and now even the dawn of practical fusion energy.
And the green code.
That's the framework around it, the coordinated policy, the investment strategy, all designed to support these high-density sources. It's driven by efficiency, smart resource management, and aiming for the smallest possible environmental footprint.
Okay.
And the main takeaway, the big finding from the research, this isn't theory anymore. This industrial policy is actively being executed. Coordinated action globally.
Right. So let's unpack that momentum.
Yeah.
The biggest news jumping out from the sources has to be fusion. It feels like it just took a massive step out of the lab.
It really did. For decades, fusion was kind of the running joke in energy circles, always 30 years away.
Always on the horizon.
Exactly. But what's fascinating now, looking at the documents, is the conversation's shifted. It's not just theoretical science projects anymore. It's becoming operational, commercial.
And this is where it gets really interesting, right? The Tennessee Valley Authority, TVA, a huge U.S. utility.
A major player.
They just issued a formal letter of intent, an LOI, to a company called Type 1 Energy.
And critically, this isn't just like our research grant. It's the first real utility-backed commercial pathway for a private fusion power plant. That's huge.
Okay, tell us more about the specifics. What does the deal look like?
Well, the details really show this is serious grid planning. The target is a 350-megawatt electric plant. They're calling it the Infinity 2 Stellarator.
350 milliready.
Okay.
And the location.
That's maybe the most telling part. It's slated for the site of the recently retired Bull Run fossil plant in Tennessee, a coal plant site.
That coal to nuclear or coal to fusion angle is fascinating. We definitely need to circle back to that. It feels like a key part of the green code.
Absolutely.
But let's talk timeline. The LOI mentions an operational pilot plant as early as the mid-2030s. Now, is that genuinely feasible, or is that more like ambitious marketing speak?
Well, based on the research team's analysis, there's reason for that optimism. It really hinges on their technology choice.
Which is?
Type 1 is building a Stellarator. Now, most of the fusion efforts you hear about use the Tokamak design, which tends to operate in pulses.
Right, I've heard of Tokamaks.
Stellarators are different. They use these incredibly complex, externally wound magnets to confine the plasma. It's a harder engineering problem up front, maybe.
But the payoff is?
Stable, continuous operation, steady state. That's the holy grail for grid power.
Ah, okay, so if TVA, a major utility, is signing on, they're not looking for bursts of power. They need something that runs constantly, baseload power.
Precisely. Continuous operation is absolutely non-negotiable if you want to provide reliable baseload power to the grid 24/7.
Makes sense.
So the fact that they chose the Stellarator design inherently signals the intent here. This project is meant to be a constant power source from day one. That choice alone sends a powerful message to investors.
And it seems like the investment world is listening. The research notes also highlighted a wider trend, didn't they? Tech giants getting involved.
Yes, making firm commitments. You saw that 200-megawatt power purchase agreement, the PPA, between Google and Commonwealth Fusion Systems.
Right, CFS and their ARC Tokamak design, also aiming for the 2030s.
Exactly. And the point is, this isn't just, corporate philanthropy anymore. This looks like real commercial demand starting to meet advanced science head on.
Okay, so fusion's getting commercial traction. Let's switch gears slightly to fission, because the policy side seems to be accelerating things there dramatically.
It is. This hot core strategy isn't just about tech. It's heavily reinforced by major geopolitical moves. The big one highlighted across the sources is this US-UK technology prosperity deal.
Technology prosperity deal. Sounds ambitious. What's the core idea?
It's essentially an attempt to create a unified regulatory powerhouse for advanced nuclear. The main goal of this transatlantic pact is to build a single pro-innovation regulatory environment
To do what specifically?
to dramatically speed up the licensing and deployment of advanced fission reactors, specifically small modular reactors, SMRs, and advanced modular reactors, AMRs.
Because historically, the bureaucracy, the regulatory hurdles, that's what killed nuclear projects, right?
Right.
Took forever, cost a fortune.
Exactly. Years, often decades. So the concrete goal the documents point to here is pretty revolutionary.
Which is?
Aligning the regulators, the U.S. Nuclear Regulatory Commission, the NRC, and the U.K.'s Office for Nuclear Regulation, the ONR, to streamline everything. They're explicitly aiming to have the time it takes for regulatory design reviews, getting it down to roughly 2 years.
Wow.
2 years.
And cutting site licensing down to just 1 year. Combine that, and you're potentially slashing 5, 6, maybe even 7 years off the historical timeline.
If they can actually pull that off.
If they can, it removes the single biggest barrier, time, and cost that has plagued nuclear deployment for decades.
That regulatory speed up is huge. But the research also flagged a major financial shift happening in the U.S., sort of a sharp pivot.
Yeah, this is where the policy certainty, or lack thereof, becomes really stark. The research team highlighted a critical financial reallocation.
Okay, what did they find?
On one hand, you see the planned cancellation and return of over $13 billion in federal funds, money that was already authorized but not yet spent. $13 billion. For what kind of projects?
Earmarked for low-density energy projects. So that's a very direct, very strategic defunding of one approach to clean energy.
That sounds politically charged.
Yeah.
Pulling $13 billion back. Is that seen as risky, betting so hard on this high-density pivot?
Well, the analysis suggests it's being balanced, or perhaps more accurately, offset by a huge incentive package specifically for advanced nuclear. That's the other side of the coin.
So taking from one pot, putting it in another.
Pretty much. They created something called the Nuclear Energy Community Tax Credit. This gives a significant 10% bonus tax credit, but only for advanced nuclear projects built in areas that already have nuclear infrastructure or a skilled nuclear workforce.
So it's targeted, not just throwing money at nuclear generally, but trying to reinforce existing nuclear hubs.
Exactly. It's targeted industrial policy, designed to build on existing strength, create economic clusters, and likely shore up political support in those key communities.
And this policy alignment connects to national security too, doesn't it? The research mentioned fuel supply.
Yes, definitely. The team cited a big contract, $1.5 billion awarded for domestic uranium enrichment, building a pilot plant called DUECE.
Upper CUECE. Okay, and the goal there.
Securing a sovereign fuel supply chain, making sure the U.S. isn't reliant on potentially unreliable foreign sources for the enriched uranium needed for both defense purposes and the growing civilian reactor fleet. Self-sufficiency is clearly a major driver here.
Okay, before we move on, just a quick note for everyone listening. We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this high-density pivot in energy policy. And if you're finding this insightful and you happen to be listening on a service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It genuinely helps us reach new listeners interested in these topics.
So picking back up, this shift towards the hot core, it's not just about electrons on the grid. The research highlights huge sustainability and community benefits, too. A lot of that comes through that Colton nuclear model we touched on with the Bull Run site for the fusion plant.
Right. Citing new advanced reactors, whether fission or fusion, on old fossil fuel sites. Economically and environmentally, it just feels smart, almost obvious, maybe.
It really does seem like a win-win-win when you look at the analysis. It delivers 3 major dividends that fit perfectly into that green code framework.
Okay, what are they?
First, brownfield redevelopment. You're using land that's already been industrialized, avoiding fights over using pristine greenfield sites. That's a common headache for big energy projects. Gone.
Makes sense. Avoids land use conflicts. What's number 2?
Infrastructure reuse. This is huge. You get to reuse those really expensive, heavy-duty grid connections that already exist at the coal plant site.
The transmission line's already there.
Exactly. High voltage lines, switch yards, the works. And the studies referenced by our team suggest this reuse can cut the capital cost of the new nuclear fusion plant by somewhere between 15% and potentially even 35%.
15 to 35% reduction in capital cost? For nuclear, where the upfront cost is the biggest challenge.
It's astronomical.
That's not just savings. That could be the difference between a project happening or not happening at all.
Absolutely. It turns a potential project killer into a massive project advantage.
Okay, so brownfield reuse, infrastructure reuse, what's the third dividend?
The third one tackles the social side, what's often called the just transition.
Hmm.
You're replacing jobs lost when the fossil fuel plant closed, often high-paying union jobs, with new, high-paying future-proof jobs in high-tech energy.
So it helps a local community that might have been hurt by the coal plant closure.
Precisely. It aims to turn a site that might represent industrial decline into a new center for economic growth and technological leadership.
That's a powerful narrative. Okay, sticking with sustainability, let's talk about the circular economy aspect. The research notes flagged an interesting agreement. Xenopower and Orano.
Yes, Sinopower and Orano. They've agreed to collaborate on recovering americium-241 from used or spent nuclear fuel.
Americium-241. Okay, so this is taking something out of nuclear waste.
Exactly. It's literally turning what we currently classify as long-term waste into a valuable, necessary resource. A perfect example of the circular economy in action.
But what is Americium-241 actually used for? Why recover it?
This is where it gets really cool, especially for space exploration and remote power needs. Americium-241 is essential for making radioisotope power systems.
Radioisotope power systems, like nuclear batteries.
That's the common term, yeah. These devices aren't reactors. They simply use the heat generated by the natural radioactive decay of the material, like Americium-241, and convert that heat directly into electricity using thermocouples. Very reliable, no moving parts.
So perfect for situations where solar power isn't practical or reliable.
Exactly. Think about powering scientific instruments, or maybe even small rovers, through the 2-week-long lunar night. That's a big challenge for NASA's Artemis program.
Right, no sun means no solar power.
Or missions going deep into space, far from the sun where solar panels become ineffective. Americium-241 has a really long half-life, over 430 years.
Wow, 430 years.
Which means it provides a very stable, very long-lasting power source. Ideal for these long-duration missions in really harsh environments. So recovering it from used fuel isn't just waste management, it's securing a strategic resource.
Okay, that's fascinating. Now, the research didn't just highlight positive momentum, it also pointed out a really stark contrast, a divergence in policy.
Yes, this was quite striking in the comparative analysis. You have these strong policy tailwinds pushing advanced nuclear forward.
The streamlined regulations, the tax credits we talked about.
Right, but then you contrast that with significant policy headwinds suddenly hitting other sectors,
Yeah.
specifically U.S. offshore wind, which was previously seen as a major growth area.
Headwinds. What kind of headwinds?
Well, the sources point to active government actions against offshore wind projects that were already permitted, already moving forward. Things like new investigations being launched, even stop work orders being issued on at least 9 different projects, according to the documents.
Stop work orders on permitted projects. That sounds chaotic for that industry.
It injects massive uncertainty, billions of dollars in investment potentially put at risk. And the contrast is the key point here.
What's the significance of that contrast, that difference in treatment?
It sends a crucial signal about policy priorities and risk. The nuclear sector, particularly advanced nuclear, is being offered clarity, acceleration, a degree of regulatory certainty it hasn't had in decades.
A clear pathway forward.
While the offshore renewable sector, in the U.S. at least, is suddenly facing profound regulatory uncertainty. That tells investors quite clearly where the government sees the strategic, reliable, long-term energy assets lying.
And that brings us back to the core technical argument underpinning this whole hot core shift, doesn't it? Density and reliability.
Exactly. Nuclear, both fission and fusion, offers continuous 247 baseload power. Power you can count on day or night, windy or calm.
And it does it with a tiny footprint compared to other sources.
A dramatically smaller footprint. The research consistently shows nuclear requires somewhere between 10 times and even 100 times less land than utility-scale wind or solar farms to produce the same amount of energy reliably.
Yet to 100 times less land.
And that land efficiency is becoming increasingly critical. It directly tackles the growing global problem of grid congestion and bottlenecks, which intermittent sources, frankly, exacerbate.
Because the grid needs power constantly, not just when the sun shines or wind blows.
Right. And dispatchable power, power you can turn on when needed, is paramount. Especially now, with massive new demands coming online, think AI, data centers, widespread electrification. High-density power reduces the strain on transmission infrastructure and avoids those huge land-use conflicts that large renewable projects often face.
Okay, so pulling all these threads together, the tech advancements, the policy shifts, the market signals, what's the consolidated outlook? What do the timelines look like now, according to the consensus across the research?
The consensus outlook seems pretty firm now. For advanced fission SMRs and AMRs, the research suggests they could realistically be online, grid connected in the late 2020s or very early 2030s.
That's soon, largely thanks to that regulatory streamlining in the US and UK.
This seems to be the key enabler, yes. And for commercial fusion, driven by that utility interest like the TVA deal and strong corporate PPAs like Google's,
Mid-2030s?
mid-2030s is now seen as a credible target for the first operational pilot plants feeding the grid, not just lab experiments, but actual power generation.
Late 2020s, early 2030s for advanced fission, mid-2030s for commercial fusion. That's a significantly faster energy transition than many were predicting even a year or two ago.
The pace has definitely picked up, driven by this coordinated policy push.
Okay, one last reminder for our listeners on YouTube. If you're finding this insightful, please do take a second to like this video, subscribe to Tomorrow Unveiled, and maybe even hit that new hype button. It really helps more people discover these discussions. And definitely turn on notifications so you don't miss our future updates.
So to really summarize this whole green code hot core shift for you, the key takeaway from the research is this. This isn't just some random evolution of technology happening in isolation.
It's deliberate.
It's a comprehensive strategic industrial policy. It's being driven by fundamental needs, energy security, geopolitical concerns about fuel supply chains, and maybe most importantly, the overwhelming, accelerating demand for reliable, dispatchable power. Power needed to meet future electrification demands, especially from things like AI, which are fundamentally reshaping the energy landscape globally.
A strategic pivot then, not just technological drift.
Exactly.
Okay, so here's a final thought to leave you with, building on the research. We've seen that the success of this high-density energy future, getting those SMRs and fusion plants built on time and on budget, seems to depend heavily on things like factory-based manufacturing, standardized designs, getting costs down through repetition.
Right, moving away from bespoke, one-off mega projects towards more predictable production lines.
So the question is, beyond the reactor technology itself, what other innovations, maybe in manufacturing, supply chains, construction techniques, even workforce training, what innovations will be the true limiting factor or the key enabler for actually achieving this new energy era on the timelines we just discussed?
That's a great question. Where are the bottlenecks around the core tech?
Something for you to mull over until our next deep dive on Tomorrow Unveiled.